In this video, we will look at conducting a drying run. Let's assume that we have prepared our materials for drying and that we know all about the facts influencing the drying process. Now we're ready to actually do some drying work. In the first step, we're going to set up the dryer to run at the proper temperature. 50 degrees to 55 degrees works well. If it's adjustable, set the airflow rate. Set it to around 0.5 meters per second. However, most home food dehydrators have preset fan speeds, so the airflow speed is not adjustable. Allow the dryer to reach steady state operation. This means that it has reached the desired set point temperature and has evened out. In the second step, load the dryer with the material to be dried. Monitor the conditions over the course of the drying period. And if you are really into it, you may wish to take observations of the temperatures and weights during the drying process, although this may not be possible to do. In the third step, test the material for doneness. This is routinely done by removing a sample and bending it to see if it's dry and leathery. If it is done, remove the material from the dryer and allow it to cool. Failure to cool the product may cause sweating in the closed container, which can lead to localized moisture pockets and potential mold growth. The fourth step is to package and store your dried product. You may wish to seal it in plastic bags that are airtight, or you may put it into plastic containers with airtight seals or glass jars with tight-fitting screw-top lids on them. And that's really all there is to it. However, some of us really want to understand what is happening in a lot more detail than this. So let's take a look at a typical drying run. In this exercise, we will look at the drying of mangoes. Rather than getting involved in too much mathematical work, we will begin by following the weight of the mangoes from the time they are placed in the dryer until they are done. The mango slices have been placed in a laboratory scale dryer, giving us the ability to follow the weight of the mangoes as they dry. And here we see the dryer. The air enters through the screen at the bottom left corner of the photograph, and you can actually see the blades of the fan which draw the air into the dryer. The air then passes over heating coils and is blown through the dryer to blow over the surface of the food material and remove the moisture. A balance assembly on top of the dryer allows us to follow the weight of the material as it is dried. Here are the mangoes at the start of the run, and you'll notice here that I have not peeled them, but normally I do remove the peels from them. And look at the plumpness of the mango slices and the somewhat shiny finish, indicating that there is moisture present. Here are the mangoes at the end of the run. You'll notice that the shininess of the surface has gone, indicating that they no longer contain moisture. You'll also notice that they have shrunken in size and have begun to curl up. The temperature of the air in the dryer and the weight of the mangoes were recorded every minute for over 20 hours in this run. That gave us over 1,200 sets of observations. We then took the results from every 15 minutes for the first 13 hours, which gave us 53 sets of results, and then we worked with them. Here's the basic plot of the weight of the mango slices versus time. And you can see that we started with 240 grams of mango slices, and over the 12 hours that I've plotted here, we can see a decline in the weight of the mango slices. If we add some grid lines to the plot, it's a little bit easier to follow, and we can see that it levels out just below 40 grams at 12 hours. So here are some important things to note. And on this graph, I've gone the full 13 hours. So the starting weight is 240 grams. The starting moisture content was 86.14% on a weight basis. That gave us a weight of water of 207.5 grams in this sample of mango slices. The weight of the solids then was 33.4 grams. At 10% moisture, we will have 90% solids, and we can then figure out the weight of the product at 10% moisture, and it is 37.1 grams. In the diagram, you can see that the weight reaches the target after about 12 to 13 hours. The dashed red line indicates the weight of the dry solids as being 33.4 grams, and the dashed green line shows us that the weight of the product at 10% moisture is 37.1 grams. We can then look at the constant rate drying period of the mangoes. During the constant rate drying period, there is a pool of moisture on the surface of the mangoes from which evaporation can occur at a constant rate. And here we see that it lasts for approximately 1.5 hours, as indicated by the vertical dashed red line. Then I drew a solid red line to follow the constant rate drying period through the first 1.5 hours, and I have extended that so it actually intersects the time axis at approximately 4.5 hours. From here we can calculate the rate of water loss. So we're going to extend a horizontal dashed green line from the initial weight of 240 grams and then drop a perpendicular there to the horizontal time axis, where the weight of the mango slices will actually be 0 grams. So the vertical line there will have a rise of 240 grams, as indicated by the solid green arrow. And the time taken to have that weight change of 240 grams for the solid red line is 4.5 hours, and we call that the run. Don't get confused about this. We are actually interested in only the solid red line at this point to figure out the rate of moisture loss. So the slope of the solid red line will give us that value. We take the rise divided by the run, which is 240 grams, divided by 4.5 hours to get 53.3 grams of water being removed per hour. And this is for the constant rate drying period. So once again, the rate of water loss is 53.3 grams of water per hour. Now we can look at the rate of water loss in the falling rate drying period. And the falling rate drying period is out there beyond the constant rate drying period, and I have arbitrarily chosen 6 hours and have drawn a vertical dashed line to intersect the experimental data curve at a time of 6 hours. Then I drew a tangent to the experimental data line as a solid red line, and I am going to take the slope of that line, which is indicated by the dashed green lines. So to do this, I have then shown that we have a rise of 110 grams and a run of 12.3 hours. So the slope of the solid red line is the rise divided by the run, which is 110 grams divided by 12.3 hours, or 8.9 grams per hour. And this is the rate of water removal during the falling rate drying period. And it is only 8.9 grams of water per hour, which is considerably less than the rate of water removal that we saw during the constant rate drying period. So getting a bit more fancy and using the dry basis moisture so we can determine a mathematical equation for the curve, we can work with this diagram. And we have substituted the grams of water per gram of dry solids, which is the dry basis moisture, on the vertical axis, and we have kept the time on the horizontal axis. And using the trend line feature on an Excel spreadsheet, we can predict that the dry basis moisture Y is equal to 6.22 times E to the minus 0.335 T for this curve. and that experimental data, shown in blue, is in very close agreement with the computer-generated trend line, shown as the red dashed line, and it is in such close agreement that the R-squared value is 0.9843. Just to explain this further, an R-squared value of 1.0000 indicates a perfect agreement between the experimental information and the computerized equation that will model this, and we're very close to having a 1.00 R-squared value. So we have close agreement in this case. Thank you very much.